Today I want to start talking about calculus. And in this segment, first of all, we'll look at derivatives and curvature, then integration, and then basic ideas of gradient, divergence, and curl. So let's start with derivatives and curvature. So firstly, the definition of the derivative of a function is the local slope or rate of change of the curve. So for example, if we have some function y equals a function of x, we write the derivative as either y prime or f prime of x or dy by dx, which is defined as the limit as delta x tends to 0 of the function evaluated at x plus delta x minus the function evaluated at x divided by delta x. Or, in terms of y, that's the same as the limit as delta x tends to y of delta y over delta x. So, for example, if I have some function y of x like this, and I'm interested in computing the gradient at this point, then the derivative is delta y divided by delta x. And in the limit, as delta y and delta x tends to 0, this tends to the slope of the gradient of the function at that point. For example, what is the slope of the curve y equals x squared minus 3x plus 10 evaluated at x equals 4? Which one of these is it? So, firstly, we can easily differentiate that function. dy by dx is generally equal to 2x minus 3. So, evaluating that function at x is equal to 4, we have dy by dx is equal to 5. And so, the answer is D. And what we've done here is this. This is the graph of that function, y as a function of x. And here we were asked to evaluate the slope at x is equal to 4, which is approximately here. So we just evaluated the gradient. So if I draw a tangent at this point, then we found that the slope of this point is 5. In other words, it's a rise of 5 over a horizontal distance of 1. And that's the simple meaning of the first derivative of a function. In the reference handbook, they have a table of derivatives and also integrals, which we'll talk about later, of various functions. And this is an extract from that table. This is a partial list. And in this table, u, v, and w are arbitrary functions of x, and a, c, and n are constants. So here are some typical derivatives. And in this, let's suppose, for example, we want to differentiate with respect to x, y is equal to sine x. So from this table, the last one here, number 16, we see that d of the general formula, d of sine u by dx, is equal to cosine u du by dx. So to make this specific to sine of x, we just substitute u is equal to x into that formula, and then we have d sine of x, which we see is equal to cosine x dx by dx, but dx by dx is 1, therefore the differential of sine x is cosine x. And you can use these simple rules to differentiate a number of different functions using this table. The other important thing that we'll use is the product rule, number 5 here, which says that the differential of the product of two functions, uv, is equal to u dv by dx plus v du by dx. And let's apply that to an example. The derivative of the function y equals sine 2x cosine x is which of these alternatives? So we're going to use our basic product rule here, and in this then, sine 2x dx is u and cosine x is v. So therefore, dy by dx is u, which is sine 2x, times the differential cosine x dx, which is minus sine x, plus v, which is cosine x again, times the derivative du by dx, derivative of sine 2x is 2 cosine 2x. So the answer is minus sine 2x sine x plus 2 cosine x cosine 2x, which is answer A. Now also we're interested in critical points on graphs. in particular maxima, minima, and inflection points. And the rules for testing for maximum and minimum and inflections are given in this extract from the handbook over on the right-hand side. So generally speaking, we have a situation like this, where here we have a local minimum, here a global minimum, in other words, an overall minimum of the function, a local maximum, and an inflection point. And to find these, first of all, the maximum and minimum occur where dy by dx is equal to 0. In other words, f prime of x is equal to 0. So at these points, the local slope of the curve is 0, in other words, horizontal. And to find whether it's a maximum point, then the second derivative with respect to x at that point is negative, less than 0, or for a minimum, the second derivative at that point is greater than 0. An inflection point is a change in the local slope. So here, for example, we have a slope here. As we move up the curve, the slope is increasing until we get to the inflection point here, and then beyond that point, the slope of the curve starts to decrease. So the slope changes sign at that point. The second derivative of the slope changes sign. Now, also, we can only differentiate with respect to one variable at a time. So if we have more than one independent variable, we have to take the partial derivative, whereby we treat all of the other variables as constants. So, for example, if we have z is some function of x and y, then the partial derivative of z with respect to x, which we write by means of these curly differential or d signs here as opposed to an ordinary d, is equal to partial d function of x and y by dx. Let me illustrate that with an example. Question is, what is the partial differential with respect to x of the function z equals x squared y plus 2x cubed y squared plus 3? Which one of these is it? Well, we can differentiate, so starting from our original function, z is equal to x squared y plus 2x cubed, etc. Then differentiating that once with respect to x, the differential of x squared is 2x. Y is treated like a constant, so just stays as y. The differential of 2x cubed is 6x squared, and y squared, again, just stays as it is, it's a constant. And the differential of a constant, finally, at the end is 0. So the answer is 2xy plus 6x squared y squared, which is answer B. Another property which is useful is the local curvature of a curve. And the curvature of a curve, denoted here by K, although later on in strength of materials, mechanics of materials, we'll use kappa, is the limit of its average curvature of the arc as the point Q approaches P. But more useful for us is to express this in terms of derivatives and rectangular coordinates. And here the equation is K, the curvature, is equal to the second derivative, d2y by dx squared, divided by 1 plus the first derivative, y prime squared, all of that raised to the 3/2 power. And another very useful property is the inverse of that. The local radius of curvature, r, is 1 over the curvature, and therefore is given by this function. And the radius of curvature is always a positive number, so we just take the absolute value there. Let's do an example on that. The radius of curvature of the function y equals 2x squared minus 3x plus 5, evaluated the point with coordinates 3 and 14, is which of these? So we're going to use this formula from the previous slide. So here's the formula that we started with. Y equals 2x squared minus 3x plus 5. So first I'll differentiate that once with respect to x. Y prime, or dy by dx, is equal to 4x minus 3. And evaluating that at the point x equals 3, I get y prime is equal to 9. The second derivative of this function, differentiating that again with respect to x, d2y by dx squared is equal to 4. So now I can plug those values into my basic equation for curvature, and I get 1 plus 9 squared to the 3 halves over 4, and the answer is 185.6. So the closest answer is A. And this completes our elementary discussion of derivatives and curvature.